as when we don't have a single CPU which is giving the instructions or addresses to the and fetching instructions from main memory and the other memory levels, but we have two or more processing units which will run instructions in parallel, so that uh, the load on one of the processors can be lessened out, and even if one of the processor is not able to work properly, then the work is not interrupted and it's done smoothly.
Okay, very good. And this is what we generally have a notion about the parallel computing systems. We talk about dual core, quad core, octa core processors, wherein we have parallel processors dividing the job amongst themselves in order to reduce the time and improve the speed. If I say I have instead of one processor, now I have two processing elements, or instead of just one having one processing element in a system, now I have two, and they are of equal capacity and they share the load equally. Obviously, I will reduce the time of computation by half for the same job and improve the speed by,
Sometimes.
yeah, two times. Very good. So but that is not just the only classification. When we talk about parallel computer classifications, we have many more. We'll discuss those today. So when we talk about parallel computers, these are those computers that emphasize parallel processing between the operations in some or the other ways. And yeah. Yes. So they can be characterized based upon data and instruction streams, forming various types of computer organizations. They can also be classified based upon computer structure, like multiple processors having separate memory units or one shared global memory unit. Or we can always classify them based upon the size of the instruction in the program, also, which is called as the grain size. The most common classification that we talk about in our day to day lives is difference classification. So, this is based upon multiplicity of instructions and data streams which are observed by the CPU during the program execution. So, if we denote I, this is I, is the instruction stream, and D as the data stream, right? The computer organizations can be basically of four main types. We can have single instruction, single data stream. So, once we talk about parallel processing, we normally, most of the times, we talk about Flint's classification. This is the most commonly used one. So, in this classification, we talk about instructions and data streams. So, how many instructions are running in parallel and how many data streams are also running in parallel, right? This might employ one computing element, processing element, or multiple processing elements also. This might employ a single memory unit or multiple memory units also, right? And the control unit also. So we might have a single control unit or we can have a multiple control unit kind of a scenario. So let's discuss it in detail. We have four main classifications. We have the single instruction and single data stream. The next one is single instruction and multiple data stream architecture. The third one is multiple instruction, single data stream architecture. Excuse me. And the last one is multiple instruction, multiple data stream architecture. Let's start with the first one. Now, if you see the first one, here we have a single instruction in one go operating on a single set of data which is taken from the memory, right? So, if we just observe this kind of an architecture, are you all getting? I hope this is not very fast. Should I repeat? I felt as if I went a little faster.
Yes, ma'am. At this slide, it was a bit fast. After
The
shifting the
previous one,
slide,
the previous one, or this
the
one?
previous one was fine, ma'am.
I'm
After
start.
shifting the slide,
Yeah, I am starting this one. Okay. So when we talk about a single instruction and single data stream architecture, this is the simplest serial computer that we have in our day-to-day lives that we use, right? So obviously, if it is a single serial kind of a computer, this will have a single processing element and one memory. In one go, the control unit will process one instruction on a single data stream. So a serial computer, a normal serial computer, as we've been discussing till now. Some basic examples are the CDC 6600, which is unpipelined but has multiple functional units. AMDOLS 470 by 6 is also has also pipeline instruction processing, but it also uses the same kind of an architecture, right? तो बड़ा सिंपल सा है. अगर हमारे पास एक ही प्रोसेसिंग एलिमेंट है और डेट मेमोरी से एक ही डेटा यूनिट इन वन गो, सो वन इंस्ट्रक्शन, सो द कंट्रोल यूनिट issues the first control signal of instruction fetch. It goes to the memory. Instruction comes, it is decoded, then on the respective data the instruction is performed. And in one go it is only one instruction which is processed to give you the results. The simplest computer that we talk about, the serial computers. Okay, is that clear?
Yes, ma'am.
So it's written also in this organization, sequential execution of instructions is performed by one CPU containing a single processing element, that is one ALU under one control unit, right? So these are conventional serial computers that process only one stream of instructions and one stream of data in one go. So the simplest one, but then just for classification, these are also mentioned. When we try to improve the speed, we will definitely try to work upon either a multiple instruction stream or a multiple data stream, right? So the next kind of Flint's classification which is there is the single instruction and multiple data stream. Now this will be kind of a, kind of a, the example would be, suppose a teacher coming to the class and instructing all the students to take down notes. So it is one instruction and multiple registers are being filled with the same instruction, right? On the same grounds, on the same analogy, if I see here, we have one control unit which issues one single instruction to multiple data streams, which are taken from multiple memory units, right, and processed using multiple processing elements, and processed using multiple processing elements. So this will be kind of an architecture wherein we have. Let me give you an example. So we can have, say, maybe an array of data, and maybe say 10 arrays of data which have to be added to the same constant, right? And then one instruction of adding that constant to the array will suffice the purpose, and that is issued by the single control unit. So this instruction goes to multiple processing elements depending upon how many multiple processing elements are required in the architecture. Each processing element now has its own data stream. So DS is greater than 1 now. So this will have its own data stream, this will have its own data stream, this will have its own data stream, right? And then they will operate on multiple data streams with the same instruction. So single instruction running on multiple data streams in parallel. I hope that's clear. Is there a doubt? You can ask me. There's no problem. Is it clear?
Yes, ma'am.
Yes.
These are very simple architectures, in wireless communication, we talk about, in the end, I'll tell you, we talk about something called MIMO structures. So similar to those we have and the computer architectures also. So the multiple processing elements here work under the control of a single control unit. It has one instruction and multiple data streams. All processing elements of this organization receive the same instruction broadcast from the control unit, as I was saying. The main memory can also be divided into modules for generating multiple data streams, acting as a distributed memory, or it can be multiple modules also. So that depends upon the kind of memory architecture we have. Do we have a big memory unit which is divided into submodules for each processing element, or each processing element can have its own memory module also. While we discuss cache coherence, this concept will come clear to you. So you will discuss that in a multiprocessor system. where every processor has its own cache, right? In that case, how do caches maintain coherence with each other? So even if it is the same instruction which is going to all the processing elements, there has to be a coordination that has to be maintained. So we'll discuss all that in detail in the next lecture. Just for your information right now, this is somehow related to coherence. Okay. All the processing elements simultaneously execute the same instruction and are said to be lockstepped together. So we can call them lockstep. Some examples are your iliac 4, your PPE, PEP, then we have the startan. I've heard about the startan, MPP, DAP, and the connection machine. So some of those we know, some of those were just in the infancy, some of those came into the market. Okay. The next architecture that we have is the multiple instruction and a single data stream architecture. Anyone who will tell me what is this architecture now? Just see, look at the diagram. It's very simple. Multiple instructions on a single data stream. So now you need to have this main memory without any subblocks, and a common memory is required. So if we are trying to improve, if we have an application wherein on the same data, say I have the data of uh, you can say your marks of my subject, for example, I have to find the average, then the variance, then the standard deviation, and all those things. So different operations on the same data stream have, if such an application comes into place, we normally employ multiple instruction, excuse me, single data stream architecture, right? So we will have a common memory, if you all can just see. So maybe we have, thousands sets of data over here, but in one go, the data will be transferred to all the processing elements as in a parallel connection to all of those in parallel, the same data stream, right? Then the first processing element maybe is performing the addition. The second processing element is performing, say, the subtraction. The nth processing element is maybe performing the multiplication. So different operations carried on same data. Definitely, if we have to issue different instructions, we need to have different control units. I hope this is clear, everyone.
Yes,
No?
ma'am.
Right, it's very very
Yes, ma'am.
simple.
Yes,
It
ma'am.
is very very simple. So from the main memory we have, we have dissociated the memory into data and instruction, for example. So the instruction stream 1 goes to control unit 1, instruction stream 2 goes to control unit 2, and instruction stream n goes to control unit n, respectively. Control unit 1 issues the respective command signals to the processing element 1. CU2 control unit 2 issues the respective operations signals to the control signals to the processing element 2, and the control unit N issues the respective control signals to the processing element N, while each one of them will be supplied with the same set of data. So on the same set of data, one is maybe performing addition, the other is performing subtraction, the last one maybe is performing multiplication, and so on. These are the most simplest examples that I'm giving. But if you talk about the day-to-day examples, uh, such an architecture is actually not very very possible. It is a very complex architecture having multiple control units in parallel, and multiple processing elements taking those control signals operating on a common data. It is difficult to implement. So the only known example of such a computer is the CC.MMP. This was built by some university. This was, yeah, uh, Carnegie Mellon University. So this was some research which was going on, and they built a prototype of this machine, but this is not yet in the market. So with more parallel instruction and a single data stream, this architecture has not yet hit the market. Right? Okay. So as I was saying, here we have multiple processing elements organized under the control of multiple control units. Each control unit is handling one instruction stream and processed through its corresponding processing element. But each processing element is processing only a single stream of data at a time. And all the processing elements are interacting with the common shared memory for the organization of a single data stream. If this is clear, I should move on to the next one. Okay,
Yes, ma'am.
all right. These are very simple ones. Just to, when we talk about parallel processing systems, these are the available architectures. The serial architecture is the very common one. So if we talk about any serial computer, it takes one instruction and then decodes it, then issues the control signals, and then processes it and produces the result on one data stream in one go. That's the most common one. Then we have the single instruction multiple data stream. That is a little easy to implement. So you just require one control element there, one control unit, and um, you have one processing element, but you can have multiple data streams which are being sorry, multiple processing elements and multiple data streams. So that is also easy to implement and is there in the market. But once we talk about your uh, this architecture, multiple instruction and single data stream, this is difficult to implement. So it looks quite good, but it is not implementable. Coming to the last one, this is the multiple instruction and multiple data stream. So again, as the name signifies, here we have the total total computing capability divided into subblocks now. So we we have different control units, each connected to a different processing element, and each capable of operating on different data stream also. So this is the best architecture. If we talk about comparison, this is the best of all the available parallel architectures, because we are dividing the total job into subparts. This is what we discussed before starting the lecture, right? So if you just see here, we have multiple control units, and each control unit is issuing a signal to a respective processing element, right? And each processing element is operating upon a separate set of data stream as well, right? So from the main memory, this is instruction stream 1, which is going to control unit 1. Instruction stream 2, it is going to control unit 2. Instruction stream n is going to control unit n, right? Each is connected to respectively processing element 1, processing element 2, and processing element n. Then it's just like, total job divided into n parts and each being operated in parallel. So the data stream 1 respectively is operated upon by this control unit 1 and processing element 1. Data stream 2 is operated upon by the processing element 2 with respect to the control signals which are issued from control unit 2, and data stream n is operated upon by the processing element n with respect to the control signals issued by the control unit n. ठीक है?
Yes, ma'am.
All right. So it is just like, having a job, and we chop it off into n parts and give each part to a respective processing element, and now the speed becomes n times because we have reduced the time by a factor of n. Okay, and this is the most efficient one. And when we talk about multiple processors in the market, we normally talk about excuse me, we normally talk about the MIMD architectures, right? So here we have multiple processing elements and multiple control units organized in the MIMD architecture. MIMD has multiple instruction streams that operate upon multiple data streams. Just a minute, yeah. So therefore, for handling multiple instruction streams, multiple control units, and multiple processing elements, excuse me, just okay. So, therefore, for handling multiple instruction streams, multiple control units and multiple processing elements are organized such that multiple processing elements are handling multiple data streams from the main memory as shown in the figure. So, the processors which work on their own data with their own instructions and tasks are executed by different processors can start. See, normally they work in master slave mode also. This you would know. So there has to be a master CPU of the all, which divides the job into the n number of CPUs, which are all connected in parallel. So usually they work in master slave mode. Okay, some examples are IBM 370 by 168. Then we have the Univac 1100 by 80 and Tandem 16, IBM 3081 and 3084 also. So the best architecture. And once, if I just try to correlate this with your wireless communication, if anybody has some interest in wireless communication, there also we have, these four architectures we have. So single, yeah, when we talk about single input and single output, here we have one antenna at transmitter and one at receiver. When we talk about single input and multiple output, so we have one transmitter and multiple receivers just to enhance the signal quality. And when we talk about MISO, we have multiple transmitters and single receiver. And this technology, the last one, is the one which we are using these days. MIMO. Do you all know about it? Have you heard about it? So this is multiple input and multiple output. We have multiple antennas at the transmitter as well as at the receiver, just to employ some diversity schemes to improve the signal quality and remove fading. So fading is loss of signal strength. If we have multiple antennas at the receiver, we can definitely improve the processor's performance. I'll just, sorry, not processor, the signal's quality. Just share the other set of slides. Okay. So I hope parallel processing systems were clear to everyone.
Yes, ma'am.
Okay, these were very simple also. Now, when we talk about parallel systems and parallel processing systems, definitely we talked about a case wherein we had multiple memories, right? We could have a case wherein we have one common memory, a big block which is shared by all the processors, or we can have multiple subunits of the memory which are being which are interconnected with all the processor modules. We can never have a standalone memory connected to a standalone processor. This is not possible. Sometimes we need to have coherence. The same data unit might be required by some other processor also. So we need to have interconnected memory modules. The diagram which is shown here, normally I draw it in the class with all the connections for my students. So I I specifically bought this thing, a stylus phone, but somehow connect नहीं हुआ. तो चलो कोई नहीं, विल ट्राई दिस. अगर नेक्स्ट टाइम हो गया तो मैं हाथ से भी करके आपको बता दूंगी. So the point is that when we have interconnected memory modules, how to interconnect them, right? And for that, we have two main configurations that we follow. We have the butterfly network and we have the beans network. Have you heard about this earlier? Yes. Have you heard about this earlier? No? Have you? No? Have you seen the diagram earlier?
Yes,
Yes,
ma'am.
ma'am.
How does it look
Yes,
like?
ma'am.
Fourier transform.
Yes, this
As
is
for the transform.
absolutely. I was about to say this. So this just looks like an FFT and it is almost the same. The connections are almost the same, just that the meanings are different now. So when we try and interconnect all the memory modules in any network, we can either follow a butterfly configuration or we can follow a beans configuration. Let us start with the first one, which is the butterfly network. What is the time? I have 15 minutes. All right. So now the first thing that we need here is 2 cross 2 switches. So all the yellow circles that you are seeing, they're all 2 cross 2 switches. What do I mean by a 2 cross 2 switch?
Two inputs and two outputs.
Very good. So if I talk about a 2 cross 2 switch, this will have two inputs and two outputs, right? So it is able to connect two inputs to two outputs, cross also and straight also. Now, when I'm talking about a butterfly network, the logic that applies here is first of all, how many rows and how many columns of interconnections are needed, right? So if I have to right now connect, say it is 0 to 15, 16 processors to 16 memory modules, I require, excuse me, n by 2 rows, right? I would have written the formula here. Yeah. So we need n by 2 rows. This means for 16, we need, for 16, we need 8 rows. Excuse me. Yes. है ना? बोलो.
Yes, ma'am.
हाँ.
Yes.
And log base 2 of n, where n is the number of processors and memory modules. See, this is always in a matrix format. Whenever we talk about processors and memory modules, it has to be the same number. So if I have to connect 16 processors to 16 memory modules, these will be the formulas that I will use. I might leave some connections vacant, but I will have to make all the connections at least, right? It can never be an odd number. It is always in a matrix format. And if I am connecting, say, 16 processors, it has to be 16 memory modules by default, right? So log base 2 of 16 becomes,
Four.
yeah, so 4 columns, right? Now, see, I have row 0, 1, 2, 3, 4, 5, 6, and 7. 8 rows and 4 columns. 1, 2, 3, and 4. ठीक है? Every
Yes, ma'am.
switch, yeah. So every switch, so wherever I have a row and a column interconnection, I will place one switch, right? So if I just try to, make it like a matrix, one column, column two, column three, and this is column four, right? हर जहाँ पे इंटरकनेक्शन होगा आपकी रो और कॉलम का, देयर यू नीड टू प्लेस वन स्विच, and with every switch you need to have two inputs and two outputs, right? So if you just realize, we'll just draw it side by side for you. Okay, so we can just start with four now. It takes a lot of time. So we have, wherever we have an interconnection, we have to place a switch. Now if we just realize, at the switch we have one input and one output is already there, right? Are you getting?
Yes, ma'am.
The row input and the
Yes,
row
ma'am.
output is already there. We need to check with the cross connection now. So at the input we will have processors 0 and 1, and at the output how to interconnect depends upon this depends upon a formula actually. So when it is a down connection, it has to be r plus 2 raised to the power column, right? And whenever it has to be an upwards connection, for the cross it has to be a minus here. So let's see how it interconnects, right? So for the first interconnection, row is 0, right? Plus column is also 0. Bolo theek hai?
Yes, ma'am.
So this gives me row number 1 as the output for a cross connection. So therefore I cross connect towards the increasing side If there is any doubt, somebody who is hesitating to ask can always send me a chat message. So there's a cross connection from row 0, column 0 to row 1. Got it, everyone? ठीक है?
Yes, ma'am.
अच्छा, हम नेक्स्ट वाला देखते हैं. So for this switch, we have two inputs, one horizontal output and one slanting output, one cross output. Done. Let's see the next one. This is row 0, no, sorry, row 1, column 0, right? If I have to see, so this is already on the downwards part. It has to, the cross connection has to go upwards, but where, that I have to see. So again, the formula that applies would be rho minus 2 raised to the power column number. So this gives me, currently rho is 1 minus 2 raised to the power 2 raised to the power column. Column is what? Tell me.
0.
Yeah. So this gives me 1 minus 1 is rho 0 now.
0.
So the cross connection which has to go upwards is now towards row 0. Got it, everyone?
Yes, ma'am.
Okay. Similarly, when we talk about this one, let's talk about this one now, right? So that your doubts also become clear. Now, if I talk about the second switch, which is there in the along the horizontal line of interconnections, this is row 0 and column 1, right? One straight connection is already made there, but I have to talk about I have to check with this cross connection wo kahan jayega. So if I just find out, this becomes row plus 2 raised to the power column. So row is 0 plus 2 raised to the power column is 1. It is column number 1. See here, this one, right? This is column 1. This was column 0. This is column 1. I'll write it. Column 0 and this is column 1. Okay, so 2 raised to the power 1, which gives me your answer. Bolo, row 2. Okay, so this means a cross connection from here has to go to row number 2. So row number 2 is here. Okay, bachcho, are you all getting?
Yes, ma'am.
All right, and let's see the next one also. So this one is again row 1 and column 1. So this will be row 1 is 1 plus 2 raised to the power 1. So makes row 3. And similarly here, if we see, this is row 3 minus 2 raised to the power 1. So 3 minus 2 makes row 1. And 2 minus 2 makes row 0. Okay, are you all getting?
Yes, ma'am.
Okay, so rest of the connections, I guess you can just jot down yourself and just realize that now with every 2x2 switch we have 2 inputs and 2 outputs. This way we have connected 16 processors to 16 memory modules. If you will try and locate, you will find out that every processor is connected to every memory module now. So you will not have any of the memory modules or any of the processor which is isolated in this network. Okay? Can you, for example, just let me know anyone? Hanji. Anyone who can tell me Is there any memory or any processor which is isolated? Speak up, bache. Let's see the memory module number 12 and connected to processor 0. For instance, I'm just picking up any one, okay? Let's see how they're interconnected now. So 12 goes here, goes here, and we were talking about the switch, right? So processor 0. So it can just go here and connect it. I hope that's clear now. So when we talk about multiple processing systems, we have multiple processors connected to multiple memory modules. We might have an MIST architecture, or we might have an SIMD architecture, or any other architecture which has multiple processors and multiple memory modules. In any of those architectures, we will have to connect all processors with all memory modules. We can never have a single memory module or a single processor as a standalone unit. That is not possible, because once we are investing into memory, we would want it to be accessible to all other processors as well. We can always maintain coherence amongst those memory modules, and that we will discuss how later on, okay? But just for your knowledge, they are all interconnected, and interconnected using either a butterfly network or a beans network. So this was your butterfly network. If it is clear, I can move on. What is the time? Just 2 minutes left. Okay, is this clear now? बोलते नहीं यार
Yes,
आप.
ma'am.
Okay. So somehow, I felt that you people don't speak in the class. I don't know why. In the face-to-face class, I used to ask questions. Anyways, you must speak up. It is for your own good. You have to sit for interviews tomorrow. This way you will gain confidence. और कोई कुछ नहीं कहता है सही है गलत है. Nobody says anything. Okay, this is your beans network. I'll discuss it next time. And there's one more configuration of the beans network. So just for right now, we will be announcing the date of the quiz soon. And syllabus for quiz is chapter 1, chapter 3 for quiz 1, chapter 2 plus chapter 3 for quiz 2, and the entire syllabus for quiz 3. Best of 2 will be considered. And in the tutorial also, we will have test in the next week. So please be prepared. This is for the entire class, not just my groups. So next week you will have test in the tutorial. You will have quiz also, and we have to conduct one quiz on Google Forms as well. Okay, that's all for today. If there are no doubts, I can end the class. ठीक है बच्चे?
Yes, ma'am.
All right.
Yes, ma'am.
ठीक है जी. Thank you.